localization. So more on localization. I guess maybe even more. Did you guys have any questions on what we talked about last time, those examples?
I mean, I do, but I don't want to consume an entire other.
I mean, those are good. Those are good questions.
Jeremy, you should keep asking, because I think that from our half-joking conversation yesterday, it sounds like we're largely on the same page about maybe not knowing what we're doing.
Let me do a warm-up problem. Okay, so let R be a domain, and consider 0 is P this prime ideal. So this prime ideal. I mean, this is the 0 ideal, so it's obviously prime. Okay. So then what is R?
If I may, we also had a notation question. The P that you're drawing, do you use that to specifically mean that it's a prime ideal, or is that just how you write your
capital P for a prime ideal? Yeah. A capital P I use, but you can use P's for other things. I like P. It's P for point and P for prime ideal.
And so when you put the underline to like denote that it's a capital, it also usually means that we're talking about the prime ideal.
Usually, yeah.
Okay.
That's the way I like to do it. Yeah.
Yeah.
Some people like to do a Fraktur P. Looks kind of like a Weierstrass P. Sometimes there's, I don't know what else people use. P is really common. Let's see if I can do a Fraktur Q.
But is that also how you write your capital P's?
I think I would write my, like, so if I said,
because
I think I
don't
put the little tail at the bottom. Like if I were to write like prime number, let's see. Prime, I'd do that. I probably don't put the little foot on. I just put the foot on so that you guys can see. So what is this? What did you guys have more specific questions about? Anyway, let's do this one. What is this? So this is SP inverse of R, right? And what's SP? SP. So SP is R set minus P. So that's a multiplicatively closed set. This is R minus 0. So this is only the 0 element. So this is essentially, this is the fraction field of R. So if you localize at the 0 ideal, then you get the fraction field of R. Okay, so this is the fraction field. Sometimes this prime ideal is called the generic point of spec P, or spec R. So were there other specific questions that you guys had?
So I was going to ask more questions about the pictures.
Okay, we can go for it.
So I think that I have a much better understanding of what's going on with the pictures, except for this business with like sort of fat lines and fat points, and when you draw like circles around points, like what exactly that means.
So like, do you understand this one? So like if I have spec R, so there's two drawings that we have. That's a good question, right? So spec R, right? And then if I have a P in here, a point or a prime ideal, right? So let's do this. So then we had R, I had spec R of P, right? This goes into spec R, right? And the way that I drew it was that, so if this is spec R, and like here is P. Then I drew it like this, right? So like this thing, does this make sense why I only drew it like a circle around this thing?
So what is the circle?
The circle is a depiction of this. So it's supposed to look like a neighborhood, right? So there's not really a locus of anything. It's a cartoon, right? So the circle this isn't a set of points, right? So this is supposed to depict a neighborhood around P. So this isn't really like literally a set, right?
But you are saying that it is a neighborhood of P?
I'm saying that you should think about it as a neighborhood of P, right? Usually all the drawings that we draw, right, they're usually about the closed points of spec R. So remember, closed points. So closed points. Okay, so this is some P in spec R. Maybe call it actually. Let's call it M in spec R, such that M closure is equal to M. So that's what a closed point is. And so, and then so the closed points of, okay, so one thing is that these M's are maximal ideals. Are maximal ideals. Right? This closure here, this closure is the closure in the Zariski topology. In Zariski topology. Right, the closed sets here of spec of R. So these are the form V of I. Sorry. V of I for an ideal I in R. All right, and these are the set of places. So these are the set of P in spec R. Where, and I'm kind of omitting the bars here. So I should really be putting bars everywhere. You know, let me just say that. So we usually write this. I'm omitting these like bars that we usually write. So this is P in spec R such that I is contained in P. Okay. So the idea is that all the functions here vanish at P.
Okay, so these are these curves that we were drawing, or that you were drawing.
Yeah, the VI is what we would do this. Okay, the other thing that I said is that for A2, okay, of C, this is spec of C of XY. Or actually, this actually works for AN, but let's just do it for A2. The closed points are just C2. Are in bijection with C2. So the maximal ideals of this ring are, you know, so maximal ideals are they look like X minus A, Y minus B for AB, an element of C. I mean, more generally, the closed points of so if I took some variety X, right, which
Can you explain what you mean by variety?
Yeah, I'm going to write it. So this is what I mean by variety. And then I'm going to mod out by some equations here. Let's do FE, E for equations, right? Then the closed points of X, right? So this is like the set of, A1 through AN and C to the N, such that, well, let's do it like this. F1 of A is equal to 0 all the way to Fe of A is equal to 0. So the closed points of these schemes that look like this, right, this topological space, really just look like the old-fashioned solutions of the polynomial equations. Okay, so here are their points, and here are their solutions of equations. And so what am I saying about this is that the way that we do drawings is we usually draw just closed points. Okay, so in these cartoons, so let me just pause here for a second so you can capture that. So in the cartoons, we usually draw closed points, since they correspond to classical points. But we do have ways of drawing generic points, right? And so like so if here's okay, so let's do A2. Again, our favorite thing. So this, and we draw it, and also we draw it in a cartoon way because we're not drawing C, we're drawing really R across R, right? Okay, and so there's other points that we could do, like, I don't know, let's do this one. So this point, this thing here, this equation, so this is a literal equation, not just, maybe I shouldn't have picked a circle because we've been using circles for other things, but I don't know. You could have a parabola. So this parabola, right? So this is y is equal to x squared, or this thing here is the vanishing of y minus x squared. So this thing corresponds to a prime ideal. In A2, but it's not a closed point.
But just to be clear, every point that this parabola is sort of like passing through, like every point that's contained in this parabola also corresponds to a maximal ideal.
Yep.
Which
Every
contains
point,
which contains this ideal, right? The
exactly.
ideal.
Exactly.
Okay.
That's exactly the case. Yeah. And so so this is a point here, M, right? And if P is, so this is some x minus a, y minus b, right? Then on this point here, you have b squared, or b is equal to a squared, right? And you also have that M is contained in, like you said, this ideal generated by this, right? This prime ideal. Oh, sorry, the other way around. That y minus x squared is contained in M. Another way to see this is like here, you have this ring, right? You can take the quotient here. Right, so this map here, this is a quotient map. And then you can take a further quotient, C of AB. So this is maybe the evaluation at the point AB. But you can see that this maximal ideal, or this evaluation map, the long one, right? So the one where it just goes to C, right? So these are particular points. So this thing, so A, B, or in C, So it could be like, e.g., A is equal to 2 and B is equal to 4, right? Okay, so this thing special. So this is the concept of specialization, right? So these variables can specialize. So the idea is that, let's see. Okay, so these variables here specialize to AB, right? So it's like this is kind of like the generic case, right? Where I don't know what X and Y are, right? But I could plug in particular A's and B's that satisfy this equation. And so we say that the terminology is that this, if P is this prime ideal, so this is P. So we'll say that, we say that M is a specialization of P, right? So it's like we have kind of like, so the idea is like this is like some sort of generic point here. So, and then as we can like, it's like a formal point, and then we can take a particular closed point and we can specialize to that closed point. Does that make sense?
Yes. I guess the only thing is like, what is it so that's given by this evaluation map, right? And what does that like do for us, I guess?
So what is the why do we care about this? Like why did we do this crazy thing? Like where we're using these extra prime ideals as points. Is that what you're asking?
Why do we do this, like this specialization? What is like?
Oh, what does it do? So like sometimes there's theorems, right, that say that things hold on an open set, right? Or there's theorems like you have a function, right? And the function can only get smaller, right, as you specialize. Or the function can only get larger as you specialize. So sometimes you can prove things about dimension things about the generic point, right? And it tells you information about the special point, the special or closed point. So it's useful it's like continuity type arguments. It's like you can prove things if you can prove things generically, then it tells you something about the specialization. Or sometimes you can prove something about the specialization and it proves something about the generic situation. So it's like if you know something that's true at one point here, right, then it ends up being true everywhere. The thing that I'm thinking about is there's a theorem that's called so I always forget upper and lower I think it's upper semi-continuity of fiber dimensions. So like I can say a little bit about this, but I mean I'll tell you. Okay, so sometimes
Tyler, can I ask a question?
Yeah.
So it seems that we keep flipping back between explaining this in terms of like A2 and prime ideal. Is there any chance that we could do a picture and kind of focus in on like the prime ideal aspect and then rewrite it and then do it like it seems that like the explanation, like every time that I'm hanging on to a little bit of one, we start explaining it in terms of like another of like kind of like I don't know, concisely like this. If I only wanted to look at this in terms of like prime ideals, like how
Just purely algebra, no geometry.
yeah, like each like kind of like each like a little more descriptive in each, because I feel like every time like I'm just like trying to get a hang of it, it's like it's kind of just moving.
I mean, I can give you the definition of specialization. So let me say, okay, so definition. So let P1 and P2 be prime ideals of R. So we say P1 or P2 is a specialization of P1 if and only if P2 contains P1. Similarly, we say P1 is a generalization of P2. Okay, so Okay, so that's the definition of generalization and specialization. But maybe it's interesting to note too that if so the closure, so the Zariski closure of let's say a single point P contains all the specializations. Of P.
So I'm a little confused as to, so we kind of defined these closed points, and then you talked about like the closure of a closed point.
Yeah.
Right? This is a risky topology.
Mm-hmm.
Like that confuses me a little bit, because
So
it's
what's
like
the
closure of a closed point. You've even said that that's just the closed point, right?
Yeah. So what's the closure of a point? Right. So the closure. So in a topological space. So if S is a subset of X, a topological space, S bar is the closure. So the closure is the smallest closed set containing S.
Yes, but didn't we say that the points were closed?
Well, I claimed that they're closed. I mean,
Oh, okay. You
so,
kind
so
of
the point here is that closed. Okay, this is the definition. Okay, this is a theorem, right? That the closed points are maximal ideals,
okay. All right. Thank you.
right? So there's a definition of what a closed point is, and the statement is that the closed points are maximal ideals, and in this case, the maximal ideals correspond to actual points.
Okay, that makes sense. Thank you.
Yeah. So, I mean, I guess you can see that the closure of a maximal ideal is itself, right? So V of M. I guess, let's see how to do this. So the closure of M, here's like a proof of this, right? So this is V of I, right, for some I. Or I mean, it's let's do it this way. Let's do it like the rigorous, the other definition. So this is the intersections of the V of ij's for j, all j's, okay, such that where ij is a subset of M, right? Well, this thing is equal to the intersection of j of, sorry, we don't do that now. Now we use the definition of the ideal. So this is V, and then we do the sum of the ij's, okay? And this thing is actually equal to, so this thing is, so we kind of want the largest ideal that contains M.
But M is maximal, so.
Yeah, so this is just V of M. V of M, right? Exactly, because M is maximal. Right, and what is this thing? So this is the set of P's in Spec R such that M contains P, or M is contained in P, right? But by maximality again, this is M by maximality. And remember, we exclude the whole ring, right, in Spec R. So the whole ring is not really an interesting ring, or not an interesting ideal for us. Okay, so this is a proof that maximal ideals give closed points. of spec R. Okay. So the other thing that you asked about was the fat pictures, right? So the fat points.
Yes.
Okay. So fat points are something different. So fat points, right? So these were things that we drew. We drew for nilpotents. So this is about infinitesimal information. So the motto here was infinitesimal. So this is how we define infinitesimal to mean information. Okay, and let me just say this is about spec of R, not, okay, so now the abuse is going to come in, not this thing, okay? Because there was a theorem before, right, that, so there's a theorem that as topological spaces, spec of A red, or spec of R reduced is homeomorphic to spec of R. Okay, and here let's recall that R reduced is where you kill all the nilpotents. R reduced is R mod the nil radical. Okay, so this is the reduction of R, and it's where it kills all the nilpotents. And nilpotents, again, a nilpotent, and then let's just recall this real quick. A and R is nilpotent if A to the n is equal to 0 for some n. Okay, and so like the classic example of a fat point is something like C of x mod x to the n, right? So this is, so if we do this, so this is, okay, so I didn't want, so this is, okay, so this thing here, we have this that goes to here. This goes from C of t. Okay, so what I'm going to draw, so this is an example of a fat point, right? So here's the point 0, and then what I drew was kind of like this little. Okay, let me draw it here. We have this little piece here. So this is this thing here. This is spec of, or I guess of C of t, or C of x mod x to the n. This is inside, and then this whole line here, this whole red line, that is spec of C of x. Okay, so the idea is that this thing factors through evaluation at 0, but it's like not quite evaluation at 0, right? This goes to C of 0. I mean, this is just C, of course. But, and then this map here is evaluation at 0. And then this map here is like, instead of taking evaluation at 0, you do some sort of Taylor series expansion at 0. So the map before, not evaluate, let's see.
Taylor, is this similar to one of the examples we kind of drew the cartoon for on Wednesday, where we were going from A2, I think, and then we were evaluating at more and more specific points, and we ended up thinking about some Taylor series around.
Yeah. So
this is that infinitesimal information we're like carrying around.
Yeah. So this thing, so the scheme itself contains information about infinitesimals, but okay, so maybe your question is like, okay, so there's these fat points, and then we have these neighborhoods, right?
Mm-hmm.
I drew these neighborhoods here. This thing in purple. Oh, how do I undo?
Just to clarify, when you say neighborhood here, you mean like a neighborhood in the Zariski topology?
No, it's not a neighborhood in the Zariski topology, actually. I mean, by a neighborhood, I mean the image of a localization at a prime ideal. So let's make a definition. Right? A neighborhood around a point. Okay, so there should be two neighborhoods. Let's call this a stock neighborhood. Okay, so I need to find some space here. So maybe I can move this over here. So this is spec R. Okay, and then maybe I need to do this. Okay, let's introduce a terminology. Oh, okay. I need to make that as thin as possible so I can fit it here. Okay, so definition. The stock neighborhood of P is the image of spec RP in spec R.
And what
Okay.
would the neighborhood of a point be in the Zariski topology, the actual neighborhood?
So like from your ordinary topological space. So open sets are massive. Okay, so in the Zariski topology, so the Zariski topology is not a separable topology. It's not Hausdorff, right? And so the neighborhoods are just huge, right? So they're just any set that doesn't, the complement of a closed set. And closed sets are really big. So it's like anything, the complement of any closed set that doesn't contain the prime ideal is what a actual neighborhood would be. I am talking about like a stock neighborhood here. And a stock neighborhood is this image here. And it's not a literal topological neighborhood. It's the image of this thing. And there's a relation between stock neighborhoods and fat points, is what I wanted to say. Maybe I can describe that.
That would be cool.
Okay. So essentially the completion. Okay, so what's the idea? So this is the fat point thing, this thing here. And so what does this have to do with what do fat points in stock neighborhoods have to do with each other? Okay, stock neighborhoods and fat points. Okay, so fat points, again, remember, they're infinitesimal thickenings. So we defined what an infinitesimal, so let's give a definition. A fat point is an infinitesimal thickening of R mod P. Right, so this is some, i.e., so we have R maps to R mod Q maps to R mod P. Okay, so then this ideal here, so Q is, so this map here, so we'll call this, so this is the quotient map for P. This is the quotient map for Q. We say, so say, QQ is the fat point. And it has the property that the kernel, so the important property. So we define, I'm going to remind you what infinitesimal thickening is here. That's what I'm doing here. So let's do an orange. Infinitesimal thickening I'm doing here. Okay. So let's do it this way, not infinitesimal. QQ is an infinitesimal thickening. If the kernel of this map to R mod P is nilpotent. Okay, so this is the definition. Okay, and so all right, so so in particular, this map here is an infinitesimal thickening. This orange thing here. Okay, it's an infinitesimal thickening of the evaluation map. Because notice that the kernel here is x to the n, right? And x to the n, if I take it in this ring, x is nilpotent in this ring. It's nilpotent. Okay. All right. So then what is the relationship between these two? So it turns out that R mod P, so we have R mod P has maximal ideal. This is what I wanted to prove today, but M mod P. And what you can consider this thing RP hat. And so this is the inverse limit of RP mod MP to the n. Okay? And the completion, so this is what's called the completion. So this thing here. Oh, whoa. So this thing is the completion of R at P. Okay, it's a local ring. It's a complete local ring. So this is the completion, and it turns out that this thing here. So these things are all these things here are all nilpotent thickenings, or infinitesimal thickenings. Okay, so this is also another word. So, okay, so let me go back to what's going on. So the thing that I told you is that, okay, so maybe I can go to an example. Okay, so let's go back to this example. Okay, so back to this example. So we had, so in A1, right, in A1, so we have a special point P. We have this point here. So P, this corresponds to the ideal X. Okay, so this corresponds to the point to 0 in C. Okay, and then there's this quotient map, right, from C of X into C of X mod the maximal ideal. Okay, this thing here is just C. And this is really like evaluation at 0, right? And then we have these nilpotent thickenings here. So let me draw, let's see. Okay, so we had these nilpotent thickenings. So we had things like, here, let's do it like this. C of X mod X to the n. Okay? These things fit into a big tower here. So this is the power series ring, right? This is the inverse limit of these things. Okay, So this is what I called RP hat. Okay. The quotient, so this is a quotient map. And then we had this localization. This is what we call the RP. Okay, this is what we call the RP. Okay, so there's kind of so the point is that this quotient factors through the localization. When I guess when it's a maximal ideal. So this quotient map here. So the point is that okay. So maybe I can draw the things in. So there's a comparison between RP hat, and the thickenings. So we have the orange stuff here. Okay, so we have the orange stuff, which is like a really infinitesimal neighborhood here. So there's this orange stuff. Orange stuff is like this. Okay. Then there is this completed neighborhood here. So I don't know what we call the completed neighborhood. What color do we use for, yeah, pink, right? There's this thing. Okay. And these are all the things that kind of like put together. It's a little bit bigger. Let me do it like. And then there's the purple thing, which is the localization. Let's see. Do we use purple? Yeah, purple. And the purple thing is here as well. So I guess this isn't really a quotient, so it's not a sub thing of this. So I usually draw the purple and pink thing the same way. I draw the purple and pink the same. But yeah, so there's this thing, there's this, and there's a comparison between this localization, which is the neighborhood, which I called the stock neighborhood, right, and the completion, okay? And the completion is built up out of all the infinitesimal thickenings. And yeah, so that's you know, that's really all I have to say about that. Yeah. Will you guys say something?
I'm processing. I'm trying to understand what. I mean, I have a bit of a question. Like, what do you mean? What does this limit mean here?
This limit. This is the literal limit. This is a limit. This is the. So what does this limit mean? So this thing here is. That's a good question. So this is the limit in normal category, in the category of rings, right? So we have. So what is this limit here? So we have C of. Let's do. We have C. We have C of x mod x squared. We have C of x mod x cubed, and then we go like this. Okay, and then you take the terminal object in the category of cones, right? So this thing here. Mod x to the n is the terminal object in the category of cones over over the diagram, right? Another way to do it is that another way is that so you can view it as the subset. So in general, if you have something like this, This is a subset of the product of the RNs. And you have it so that, but this is equal to the set of, A0, A1, blah, blah, where AI plus 1 maps to AI under transition maps. In the diagram. So that's another way to do it. And it turns out that this thing is isomorphic to the power series ring here. So I need to give you guys your exercise, your quiz. And I'll stick around if you guys have more questions. So the quiz question was, where did I put it? So it's number 35 from the worksheet. So here's the quiz question. And you can do this one really quickly. So if you understand what's going on, it should go really quick. So this is number 35, by the way. And it says that, so part A is find the smallest n.
Taylor, I don't know if
You can't see your screen right now.
Oh, you can't see my screen right now? Okay, so find the smallest n such that there is an n by n matrix with q coefficients satisfying a to the 9th is equal to I, but not satisfying, but a to the I is not equal to I for 1 less than or equal to I less than or equal to 8. Okay, part B is to exhibit the matrix. Okay, and then part C is find the smallest n and such that there exists two non-similar matrices. A and B with satisfying the same conditions. All right. Okay, so I'm going to stop the video here and let me know if you guys have any questions. And I'm gonna post these notes into the chat.